So we're starting. Cell phones should be away. Okay. Number 14 was a problem that a lot of people had a hard time with. So I just want to go over that one. And then that one is very similar to 27 through 30. So my guess is we struggled with those. So let's talk about them. All right. So it asked if the inverse, if f of x was an invertible function, which means that once you find the inverse itself is a function. So what I went ahead and did is I looked for points for the original absolute value graph. I switched the x and the y coordinates. I redrew it. Now I'm going to ignore the original graph. Is this graph a function, y or y not? No, why not? Does not pass the vertical line test. So when I check to see when I check to see if f of x is an invertible function, I don't even look at f of x, I look at its inverse, okay? So go ahead and label this on your paper. That is f of x. This is f inverse of x. So I've got my function, I've got my inverse. When I cover up my function and just look at the inverse is not a function. So is f of x an invertible function? The answer is no, because the inverse is not a function. Explain why it isn't a function. It doesn't pass the vertical line test. So this means that some of the x values, some of the inputs, do not have predictable outputs. So if I plug in an x value of 3, am I going to get the same answer every time? No, you could get 0 out of that, or you could get -2 out of that. It's not predictable. Two different answers, okay? All right, so they said to restrict the domain so that the restricted graph would be invertible. So we can't keep the whole V shape to have an invertible graph. You want to keep half of it. Now, most of you guys, I said it was okay if we just said, let's keep the left half, or let's keep the right half. But if we want to restrict the domain, how should we write that? Because right now the domain is -infinity to +infinity. It goes left forever, it goes right forever. So we can make it an inequality. So if I want to keep the left side, what should I write? If we kept the left side, less than. So if we want to keep the left side, we'll go ahead and do both options. If we want to keep the left side, then we would say that our restricted domain would be -infinity to -1, or if you were writing this as an inequality, you could say x is less than or equal to -1. That would keep the left side. What does that do to the inverse? If you keep the left side, which one does it keep? It doesn't keep the top. It keeps the bottom, yeah. So whenever we do inverses, we're reflecting over the line y equals x. So if you went through and drew this dotted line in all of your pictures, you would notice that they had symmetry, like they got folded over that line. And so if we have the left side is what we're keeping, then the bottom side is what it keeps of the inverse. So we're going to say it keeps the bottom. Really, for you guys to be able to draw it again, I should have given you another graph to be able to draw it again. Okay, what if we decided to keep the right side instead? Then the domain would be not 1 though, -1. So the domain would be -1 to infinity, or if you wrote it as an inequality, you could say x is greater than or equal to -1. And then, so if we're keeping the right side, then what part does that keep of the inverse? The top. So when you fold it over, it's right there. So that would keep the top. Now, what we did is we tried to keep as much of it as we possibly could. But technically, you couldn't just say left side or right side. I could even say keep x is less than or equal to -2. And that would have cut off a little bit more than half, but it still would have been a function. Does that make sense? So there are infinitely many ways you could restrict the domain to have something that was invertible. But the point is that if we restrict it, if we cut part of it off, then we're going to be able to have an invertible function, because whatever we reflect over the line y equals x, or whatever we find the inverse of, would then pass the vertical line test. Does that make sense? So you can think of invertible means vertical line test. It passes the vertical line test. Does that make sense? Yes, Ms. Rice? Marvelous. All right, let's turn the page over here. So if we were to sketch a little graph of this, this is a parabola. What has happened to the parabola? What's the transformation? Left 3. Okay. So it looks something like this. So that means if I reflect it, it's going to look something like this. Okay. Is it invertible right now? No, it's not going to pass the vertical line test when we find the inverse. So they said limit the domain so that the inverse can be found and so that it will be a function. Okay, so how should we limit the domain of the original graph so that its inverse is actually a function? We can do it just like we did before. We can think about left side versus right side. So which side do you guys want to keep, the left side or the right side? The right side. Okay, so if I keep the right side, that means I'm starting at the vertex and going towards the right. Okay? So what's the domain? The domain of the original function is negative infinity to positive infinity. But when I cut it in half and I only keep the right side, what am I keeping? Negative 3 to infinity. Okay? And actually, let's go back here. I made a little mistake and nobody caught it. It was on these ones right here. Bracket, yeah. We had the equal to with the inequality, but we forgot the equal to with the interval notation. Okay, so let's go back over here. What should we write for the domain? Bracket. I wrote a parenthesis again. Bracket, you forgive me? Negative 3 to infinity. Okay. So we kept the right side. Now, when we find the inverse, what does that mean we're going to keep? Are we going to keep the top half or the bottom half? Top half. Because if you look at it when it reflects over that line, it's going to match up with this part right here. That's what makes it look like it got folded in half. Okay. So they want us to go through and actually do the process for finding an inverse. So I'm going to start off by trading my x and my y. And what should I do next? Cube it? Square root it, yeah. So we're going to square root each side. And what happens when I do a square root? What am I supposed to put in front of the square root? If you square root 4, the square root of 4 is more than just 2, plus or minus 2. So whenever you are the person taking the square root, you're supposed to put a plus minus in front of it. If the square root is already written on paper, then you just do the positive version or the negative version, whatever they had. But anytime you are the person who's doing it, you're supposed to put a plus minus. So we're supposed to say plus minus the square root of x equals y plus 3. And then subtract 3. So we have plus minus the square root of x minus 3 equals y. And then we have to think about this graph represents what's down here with the plus and the minus. Both of them represent the whole picture that I drew in pencil. Which one represents the blue only? Is it the plus version or the minus version? It's the plus version. So square root graphs typically go up, right? So this is saying if I do the plus version, it's a square root graph that goes up. It's been shifted down 3. If I do the minus version, it's a square root graph that's been shifted down 3, but it's upside down. And our blue graph is right side up. Okay, so we're going to say the inverse function is y inverse equals square root x minus 3. So there's our limited domain. This is the inverse that goes with it. Now, if I switch my answer and I say that my limited domain is negative infinity to negative 3, if I switch my answer to use the left side instead, this side over here, then that would switch my inverse to being the negative version because I would want the upside down square root graph. So these two answers, that's one valid solution. The other valid solution is to do this one right here. How are your brains? Chilling? Okay. Let's try the next one. All right. So how do I draw this quadratic? Right sec. So it's going to be like this. So when I draw the inverse is something like this. They would kind of cross over each other. Kind of weird. My drawing's not perfect. It should be higher up. Let me go ahead and fix that. Okay. What side do you guys want to keep from the original? Want to keep the right side or the left side? Left side this time. So we'll say here's the vertex. We're going to keep the left side. So the original domain was negative infinity to positive infinity, but we're restricting the domain. And so what is the restricted domain? Negative infinity to 6, because the x-coordinate of the vertex is at 6. Okay, so negative infinity to 6 is our domain. So we're restricting it so we know what our inverse function should be. Well, because they go together. So for our answers to be right, I either have to have these two answers as a pair or these two answers as a pair. But I can't mix and match. If I mix and match, I'm wrong. So if I said keep the right side of the original parabola but keep the bottom of the inverse, then I'd be wrong because that didn't actually reflect over there. So the blue reflected to blue, so these are the answers if I kept the blue. The purple reflects to purple, so those are the answers if I kept the purple. If I keep one of each, it looks like I sincerely tried, but I don't understand what I'm doing. Yeah. Okay, so our domain is from negative infinity to positive 6. Are we keeping, of the inverse, are we keeping the top or the bottom? The bottom, so that's what would make that reflection, is if we kept the bottom. Okay, so let's go through and find the inverse by hand. So we're going to say x equals y minus 6 squared. And what do I do? Square root. And then what do I do when I take the square root? Plus minus. So plus minus root x equals y minus 6. Add the 6. Plus minus root x plus 6 equals y. And then I want the square root graph that has been shifted up 6 and is upside down. So I'm using the minus version this time. So I'm going to say y inverse equals the negative version that's been shifted up 6. So there's my inverse function. There's the restricted domain. Those answers go together. Or if I wanted to do the other version was to keep the right side. So what's the restricted domain for the right side? 6 to infinity. And then what's the inverse function that matches up with it? The positive version, square root x plus 6. Okay, so 29 and 30 are kind of like the backwards version of that. So if we were to start off with 29, how do I graph square root x minus 7? Start at 0, negative 7, so it's been shifted down 7. And it doesn't have a stretch, it doesn't move left and right, it doesn't do anything else, so it's just like a normal square root graph. It looks like this. Okay, so let's go ahead and draw our dotted line. All right, so this is the point 0, negative 7. So what's the vertex of our quadratic? Negative 7, 0. So our quadratic is at negative 7, 0. And then when we draw it, are we drawing the left side of the quadratic or the right side of the quadratic? The right side. So if I try to draw the left side, see how this would not have that symmetry? It doesn't look like I folded it in half. But if I draw the right side, then I can see it has that symmetry. It looks like I folded it in half. Okay, so we know that our answer is going to be a quadratic. We know that it has to be the right side of the quadratic. Does that make sense? It has to be the right side. Okay, so let's go ahead and we're going to trade the x and the y.
So do you know that it's a parabola?
Because I know that square root of x and x squared are inverses of each other. Just like I know that x cubed and cube root x are inverses of each other. Does that make sense?
Yeah, but if it says y and not like the inverse version, how do you know it was? Like, how do you know?
Sometimes you might have to just start off the problem by switching the x and the y and solving for y to see what the inverse function even is. Like the inverse of a straight line is another straight line. So sometimes they don't feel that like opposite, but square roots and quadratics are opposites of each other. Yeah. Let me finish this. All right, so we traded the x and the y. What do we have to do next? Add the 7. So x plus 7 equals square root y. Square both sides. Okay. Now, I cannot say this is my final answer because this includes the whole parabola. So what else do I need in my final answer to show that I'm only using the right side of the parabola? I need to say that the domain is...
And it's inverse?
Yep, it's going to be inverse. Is negative 7 to infinity. So that's me specifying, yes, I found the inverse, but to make sure that it's an actual inverse, I should only keep half of it. I shouldn't have the whole thing because the original graph didn't have the whole thing. Okay, let's try the next one. So how do we draft this one? Left 5. Okay, it's a square root graph that looks like that. Left 5. So if the locator point of this one, kind of like Vertex, but not, if the locator point is at negative 5, 0, then where is the parabola going to be? Negative 5, 0. 0, negative 5. So the parabola is over here. Should I do the left side or should I do the right side? The right side. Does that make sense? So we're using the dotted line to help us figure out how it should work. It should look like that. So I can see that they look like they've been folded over. Okay, so let's go through and find it by hand. X equals square root of y plus 5. And what do I do next? Square it. So x squared equals y plus 5. Subtract the 5. Okay, I'm doing my inverse notation, and then I'm being careful to say we're only using the right side of that parabola. So what should I write? Domain is 0 to infinity because we want the x coordinate on the y coordinate. So 0 to infinity. Okay. These are excellent bonus questions. Just saying. Okay. So if you're done with your packet, go ahead and turn it in. For the rest of the period, we are going to work on our test review because we have a test tomorrow. How wonderful. How wonderful. I'm so excited. Anyone else excited for our test tomorrow? Your faces look so happy.